In this section, we're going to examine compound probabilities that will use one of three important compound words, actually. We're going to look at the words or, and at least. So this problem that's staring at us on the screen looks like an and type problem, and you'll see what I mean in a minute. What I want to do is I'm going to redo the counting method where I use the tree diagram to count out all the possible outcomes that you could have when you flip three coins. So I'm going to go ahead and start with flip number one, either heads or tails. So there's the first flip. And I'm going to continue on. Heads, tails, down here as well. Let's do, I think, that far. Heads, tails. So that was the second flip, and now the third flip. So I have heads, tails after that flip, and then we have heads and tails after that flip down there. And then let's see if I got enough space. You can get a little, space gets a little crowded on these things if you don't do them perfectly. So let me get my little heads, tails, heads. Let me put tails down there. All right, now let me follow along with each of these paths starting from here. If I go along this top one here, I have an H, H, H. So I didn't put an H there, but that is heads. That's the three heads. That's, well, they're not asking us that, but the probability of three heads is actually the same as the probability of three tails. Let me move on to the next one here. We have H, H, T. Then we have heads, tails, heads. And then finally heads, tails, tails. Now let's move on to the bottom half. Here we have tails, heads, heads. Then we've got tails, heads, tails. And then tails, tails, heads. And the very last one, the one that they actually asked us about, is what is all tails? So the answer is easy from this. We see that there's only one situation out of a total of 8 of them where there are all tails. So the answer to this question is 1/8. However, I want to show you an alternative that uses something called independence. When you flip a coin, are we flipping 3 fair coins? Let's call them coins 1, 2, and 3. So here is coin 1, coin 2, and coin 3. Each of these coins can be either heads or tails. And in fact, when you toss these, coin 1 will be heads or tails regardless of what coins 2 or 3 are. And coin 2 will be heads or tails no matter what the other 2 coins are. What I'm getting at is whatever the value of one coin is, whether it's heads or tails, that doesn't change the probabilities of any of the other coins coming up either heads or tails. So they act independently of each other, is what I'm saying. So if I want to get tails each time, what I can do is set up a thing like this. Then coin 1, if I want it to be tails, has a 1/2 probability of occurring. If I want the second coin also to be tails, that has a 1/2 probability of occurring, and the same for coin number 3. And when you multiply these fractions, you multiply across. So 1 times 1 times 1 gives me 1, and then in the denominator, 2 times 2 times 2. As an example, suppose you have 5 shirts and 3 pairs of pants. Not only that, you prefer black for almost everything you wear. So 4 out of your 5 pants or shirts are black, and 2 out of your 3 pants are black. So we have only 1 white shirt and we have 1 white pants. So if you reach in without looking and grab pants and a shirt, what's the probability they'll be both white? So what you can do is this. Set it up like I did before. We're going to be taking a look at the shirt and also the pants. So the shirt, to get a white shirt, so we want that to be white and the pants to be white. So to get a white shirt, that is 1 out of 5, since we're told we only have 1 white shirt. And the pants, we only have 1 white pant, so that is 1 out of 3 pants. And then as before, multiply these two fractions, you get 1 over 15. Let me grab a couple of definitions up here. Let A and B be events. A and B are independent. That's the vocabulary word here. These events are independent if the occurrence of one event does not affect the probability of the other event from occurring. And when that happens, let me call it, I don't know what to call it. So if A and B are independent, then the probability of A and B equals the probability of A times the probability of B. And these first two examples have shown exactly this property. Some examples, common examples of independent events are like flipping coins. As I said, one coin does not know the value of the other coins. So whatever one coin turns up, it does not influence the probability of the other coins at all. Drawing a card, if you replace it. If you draw a card and you don't replace it, you'll leave a deck with 51 cards, and that alters the probability of subsequent draws. So if you want a game where you can draw the card and not alter the probability, then each time you draw the card, you need to put it back so that you still have 52. Additionally, to make sure that you're still dealing with randomness, every time you put the card back, you'll have to reshuffle the deck to make sure that things are out of order. And rolling dice too. The value of one die does not know the value of the other die. So there's an important thing that people often say. If you take and roll a die, say you roll a die and you get 3 a bunch of times in a row. If you should get a 3 7, 8, 9 times in a row, then after these 9 throws, you have the die in your hand. What is the probability that the next roll will be a 3? Well, it's still 1 out of 6, just like the previous ones. However, seeing 3 come up like 9 times in a row will start to make you think that there's something wrong with the die. Here we're rolling a die twice. So we want to know what is the probability of first getting a 3 and then getting a 4. So the way we could look at it is we could have roll number 1, and we want that to be a 3, and then roll number 2, we want that to be a 4. To get any particular number on a die, it's 1 out of 6, and the same over here, which is 1 out of 6. So the probability of getting that exact 3, 4 in a row like that is 1 out of 36. Here's an example where we use relative frequencies again. Here we have every 100 years we have a flood of this place. So what we're going to assume is that for every year we have a 0.01 probability of a flood. And in the same in 2 consecutive years. So what is the probability that that will happen in 2 consecutive years? Well, I need to know that the events are independent. 1 year to the next are independent, and that is exactly what they're doing here with this whole sentence. They're assuming that the flood in 1 year does not affect the likelihood of a flood in the next year. They are exactly telling us that these events are independent. So with that then, let's take a look occurring in 2 consecutive years. So we can have the first year, we want a flood, and the second year, a flood. So the first year, it's 0.01 times 0.01 again, and I think you'll find that that's 0.0001. Dependent events. The easiest way is to show this with drawing a card from a deck. So consider drawing 2 cards. All right, so let's take a look at independent versus dependence. So if we draw 2 cards, let's take a look at the independent case. Draw 1 card, record its value, put it back, and reshuffle. Draw a second card. Now, what happens here is because you put the first card back and reshuffled, you still have 52 cards in the deck. So whatever card that I want still has a 1 out of 52 chance of occurring. Now, dependent would work this way. Draw a card, but don't put it back. Draw a second card. So with that, once you draw the second card, now the chances of that card coming up, any particular card, is 1 out of 51. So in this one, both cards have a 1 out of 52 chance for both cards. But here, we have a 1 out of 52 chance for the first card, and only a 1 out of a 51 chance for the second card. So you can see that the drawing of the first card has affected the probabilities of the cards still left in the deck. Definition. And it is going to be the probability of B given A. This is the probability of B occurring if A has already occurred. Now in this example, I'm drawing 2 cards from a deck of 52. So we can think of it as there being a first card and a second card. So I want the first card to be red and I want the second card to be black. So I can set up my thing as I have all the other problems. I have the first one I want to be red and the second one I want to be black. Well, the red ones, since there's 52 cards and there's 26 red ones, this is 1 out of 2. Or you could do 26 out of, I think I'm going to leave it like that actually, because simplifying is not always in the best interest. So there are 26 red cards out of 52. Now that card does not put back. So there's only 51 cards for black. Well, I didn't choose a black card on the first one, so I still know I have 26 of them out of 51 that are left over. Now when you multiply these two things together, remember, you multiply the numerators together and you multiply the denominators together. So the numerators, I'm going to have 26 times 26, which is 676. And then 52 times 51, 2652. If you want any of these, turn them into decimals if you like. I'm leaving them as fractions because I noticed that the homework requires sometimes for you to leave them as fractions. But it's easy to put these as decimals. This example, we're referencing the game of bingo, and you're drawing labeled buttons from a bin at random without replacing those drawn. So you pull one out and you have one less button in the bin after you've used it. Okay, so you're not putting them back. That's the important thing. There are 75 buttons, so we've got 15 for each of the letters B, I, N, G, and O. So what is the probability of drawing 2 B buttons on the first 2 selections? So let's take a look here. So we want the first selection, we want it to be B. Well, we know there's 15 of those out of a total of 75. And then we also want the second one to be B. And on that one, since the first one was the B, there's only 14 of them left. And similarly, since you did take a button away for the first one, there's only 74 buttons left. So 15 times 14, 210. 75 times 74, 5550. Next we have what's called a mathematical theorem. You can take it as a true fact. We're going to let A and B be dependent events. In that case, the probability of A and B equals the probability of A times the probability of B given A. Now recall, if A and B are independent, then what we had was the probability of A and B was equal to the probability of A times the probability of B. Now this here, this B given A, if B is independent of A, then this probability is just going to be B. So you could technically use this one formula for everything, and when B and A are independent, this formula will just work out correctly. Or you can use the two different formulas. So these are dependent events and these are independent events. That's what it means mathematically when we do our computations. Here we've got a 3-person jury is to be selected at random from a pool that has 6 men and 6 women. what's the probability of selecting an all-male jury? So what we want to do then is let's take a look at the three jurors. We'll call them Juror 1, Juror 2, and Juror 3. And we want them all to be male, so we'll have male, male, male. Now the first male that is chosen, there's 6 of them out of a total of 12. After that male is selected, there's only 5 males left out of 11. And then after that second male has been chosen, there's only 4 males left out of 10. And so this equals 120 out of 1,320. Our next concept is a word called or. So as usual, let A and B be events. A and B are called non-overlapping if they cannot occur at the same time. So what we have in this case, if I look at A or B, that equals the probability of A plus the probability of B. However, if A and B have overlap, that means some of the events in A and some of the events in B are equal to each other. So if A and B have some overlap, then we have the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. The deal is this: if we look at this last piece, probability of A and B, if these two things are non-overlapping, this probability will equal 0 and it drops out anyways, and you end up getting the first equation. Here's an example of non-overlapping events. We have, when you roll a single die, either a 2 comes up or a 3 comes up or some other number. Fact is, you can't have a 2 come up at the same time as a 3. So these two things are non-overlapping. So let me make sure that I put that as a note. What that means is that if I look at the probability of a 2 or 3, I can use the second or the first of the equations above. And since there's no overlapping, I don't have the part that had the subtracted part. The probability of getting any one number on a die is 1 out of 6. So both of these are 1 out of 6. And the total probability then is 2 out of 6. Okay, we have 8 people in a room, 4 men, 4 women, 2 Democrats, and 2 Republicans of each. All right, what we want to do is we want to select one person at random from this room. What is the probability that you will select either a woman, so either a woman or a Democrat? So let's take a look at this. Probability of a W or Democrat. So this is the probability of a woman plus the probability of a Democrat minus the probability of being a woman and a Democrat. This formula will work no matter what, but I don't know if there's any overlap. I'll see if there is when I work this problem. So the probability of being a woman, I told you there's 4 men and 4 women, so that's 4 out of 8. And now the probability of being Democrat. Well, there's 2 male Democrats and 2 female Democrats, so that's also 4 out of 8. Now, is there any overlap between women and Democrats? We are told that there are 2 Democratic women, so that's 2 out of 8. Remember, when you add up fractions, you simply add along the numerators. So I have 4 plus 4 minus 2 will give me 6 over 8. The next concept is at least 1. So I want you to think about something. What is the probability of at least 1 plus the probability of 0? Well, it equals 1. What I'm getting at here is when you talk about a collection of things, any kind of a collection, if I say I either have none or I have at least one of them. So together, those two states, having none or having one or more, constitutes 100% of the possibilities. So what I can do then is I can do the probability of at least 1 can equal 1 minus the probability of none. That's a better one than what I've used before. To illustrate this last property here, this at least property, we want to find the probability of getting at least one head when you toss 3 coins. So I know this. I know that the probability of at least one head, that's going to equal 1 minus the probability of 0 heads. So that's 1 minus the probability of all tails. Now we could go back to the chart if we want to, but the fact is I can do the probability of all tails means that I would have a tail on the first one, a tail on the second one, and a tail on the first one. So the first coin would be a tail. The second coin would also be a tail. And the third coin would also be a tail. Each of those tails can happen at a probability of 1/2. So this whole thing equals 1/8. So coming back to my equation, this guy here, let me come down here and finish it off. The probability of at least 1h equals 1 minus the probability of 0h, which is all tails, 1 minus 1 over 8. And to do this subtraction, I'm going to rewrite 1 as 8 over 8. And then when you combine these two fractions, we get a final answer of 7 over 8. All right, this is the 100-year flood problem again, but revisited. Suppose we do have this 100-year flood and we have a 0.01 chance of occurring in any given year. Flooding can occur at a chance of 0.01. What is the probability that we will have at least one flood in the next 100 years? So I will use my formula. So the probability of at least one flood equals 1 minus the probability of 0 floods. Let's think about that now. 0 floods means that you didn't have a flood for 100 years. So that means that for the first year, you had no flood. Well, the chances of not having a flood is 0.99. Now, we made this assumption here the independence assumption. So I can use this multiplication property. So my second one is also going to be 0.99. That was for the second year. So what I'm doing here is the probability of 0 floods is equal to this stuff here. And in the third year, 0.99 over, well, it's the third year. No flood that year. This continues throughout all 100 years. So you even get it at the very end when you get to the 100th year of no flooding. So, and these are all multiplied together. So I have a total of, well, I put the multiplication down there. I guess it's fine. Let me take it from up here. So then what we're going to have is 0.99 times 0.99 times 0.99 all the way to the 100 times. So we can do this by doing 0.99 raised to the 100th power. 0.99. Now on this calculator here, the x to the y button is what you use for an exponent. And I'll put 100 and I'll hit enter. So I'm going to go to 3 decimal places here. I get 0.366. So remember, that's not the answer to the question. We just found the probability of 0 floods. So come back here then. If we want the probability of at least 1 flood, then we take 1 minus 0.366. I think that is 0.634. In our last example, we buy 10 lottery tickets, and you win. A single ticket has a chance of winning of 1 in 9. So your chance of losing is 8 in 9. So what is the probability that you will have at least 1 winning ticket among the 10 tickets? So I'm going to say the probability of at least 1 winner equals 1 minus the probability of 0 winners. Same as before, I'll put it down here. The probability of 0 winners, that means on the first one, you had a loser, and your chances of losing are 8 out of 9. On the second one, also a loser, also 8 out of 9. The third one, loser, 8 out of 9. Well, I think you're getting the idea here. I'm not going to write all of them down. And then finally we bought 10 of them. So the 10th was also a loser, 8 out of 9. These are all multiplied together. So we have 8 over 9 to the 10th. Now your calculator is probably going to do a decimal. If, however, you want to get a fraction, you can do this as 8 to the 10th divided by 9 to the 10th. So let me go ahead and do that fraction. 8 raised to the 10th power. Wow, look at that thing. 9 raised to the 10th power. Well, I've decided to leave all my digits there, so to solve this then, I'll go back up here. I have 1 minus 1073,741,824. That's the numerator. And that's divided by 3,486,784,401. I'll finish it off by rewriting the 1 as 3,486,784,401 divided by that exact same number, and subtracting from it the 1,073,741,824. So all I have to do is subtract the numerators together. The denominator will stay the same, so let me go ahead and put that in. And so all I need to do is take this 3 million number, or was it 3 billion, and subtract the 1 million number from it. Well, luckily I've already got that in there, so I can just subtract from there, minus 1,073,741,824, and I get that number. And once again, I let my calculator help me out a little bit with the writing of the number. You don't have to simplify if you don't want to. My guess is if you encounter a problem like this in the homework, they will let you go decimals all the way since you have so many things being taken to a large power.